Our next speaker is my pleasure to introduce you to our next speaker. It's Professor Amir Caldeira from the University of Campinas. And this is his first lecture, so please, Amir, you can start.
Thank you. Good morning all. And what I'm going to talk about is macroscopic quantum phenomena and quantum dissipation. And I should add, it's a review talk. So I'll be touching upon many issues that we addressed for the last maybe 45 years. And so the plan is the following. I will start with the very basic of superconductivity. I will talk about superconducting devices, and I will try to analyze this idea of macroscopic quantum phenomena. And lecture 2, I'll talk about quantum dissipation. Why? Because as we will see that dissipation is very important in all these systems here, especially as superconducting devices. And then we'll talk about models and applications for that. And finally, we'll address some experimental realizations and talk about superconducting qubits. So let's start. Well, but mind you, I will not do any sort of a microscopic superconductivity. I will be addressing something very more. Right? So, and the main idea is the following. I will first talk about this theory that's the London theory of superconductivity that we just started with some phenomenological equations trying to describe these two main characteristics of superconductivity: the transport of charge with no resistance and perfect dynamism, so the Meissner effect. And the idea is the following: what London did was to propose a couple of phenomenological equations, and these equations for the electric field. Instead of the Ohm's law, what we have is the electric field proportional to the derivative of the supercurrent or supercurrent density, and this supercurrent density will generate a magnetic field. So these are purely phenomenological, because this one here, if I have, for instance, zero field, I can still have some sort of constant current density. And the second one, if I use this equation combined with this Ampere's law, what we have is that you take the rotation of the second equations, then we end up something like this, which is the Laplacian of B, and B divided by this length square, and that's the so-called the London penetration depth. And this is related to this big lambda, this capital lambda, through this equation here. And so these are the basic London equations. So pure phenomenological. And so if we just analyze this equation here, right, this resulting equation. So what we have is that the magnetic field will avoid completely the superconducting sample, and so B will be a zero inside the sample, and we have this penetration depth here, which tells us exactly how the field penetrates the sample, and that's the critical field that will destroy superconductivity. So if we are below a given temperature, it starts to increase, and it will be maximum at zero temperature. So that's basically the idea that we can describe. So we can describe the basics of superconductivity with those two very simple equations. Now, the point is, if we go on with those equations, you see the first one, which is this one here, and if there is no scalar potential, what we have is that E is given by this well-known expression. So in this way, we can relate the superconducting current density to the vector potential through this relation. And so what we can say is that we have sort of free choice for this A naught, which is only a function of position, no time dependence there. And And this is very, very dangerous. Okay, so what you can do here is the following. We can just assume that we can decompose this A naught in terms of these components of the current density, and if there is no charge flowing out of the specimen, we can say that this A naught is zero, and that's the so-called London gauge. And in this way here, we can say that the superconducting current density is proportional to the vector potential. So that's the result that we have from London equations. So we can actually resume or combine the two London equations through this one here. And now, there is another way we can get the same sort of equation. We can do the following. There is a very old theorem by Bloch. That's not the Bloch theorem of solid state physics, that you have this wave function for the periodic potential. It's something else. It says that for instance, any many Fermi system, the ground state of the system, doesn't really matter what the system you have, will have this, the average of the ground state of the momentum will be zero, right? So the true genuine ground state of the system. And if we do that, and if we apply that to a system in a magnetic field, we say that P is equal to the mechanical momentum plus the field momentum. And mind you, M and E here, we should regard those as sort of effective mass and effective charge of the super electron. This charge, the carrier, which is responsible for the superconductivity. But then, usually, you find that as the electronic mass and the charge of the electron. And so, if we just combine the two, and we say that the average here is zero, so we claim that this is the average of the mechanical momentum, which can be related to the density of current, is given by this expression. So, and we multiply that by NST, and that's the sort of relation that we have. Again, Js proportional to the vector potential, and so in this way here we can, we can compare that with the previous equation, and we can extract the value of lambda L in terms of this mass, charge, and so on. And density of super carriers, right? And that's the, as we know, I will try to avoid disturbance, saying that that's the density of Cooper pairs, because we know that these super carriers are pairs of electrons. So, that's the sort of equation that we have here. And again, we got that from, that was the first quantum mechanical information that I gave you, that that's the ground state of the electronic system must have this P equals zero. So in this way, we can say that if we just use the current density given by the wave function of the ground state of the system, we'll have this well-known expression from quantum mechanics. And of course, this guy here must be zero in the absence of the field of the vector potential. So in this case here, if I change this, if I turn on the vector potential, we have to replace P by this P minus, this combination here. And psi naught will be modified to a disturbed ground state, which is psi. And so in this way here, our current density will be given by this expression, which is the same as that, minus this term proportional to the vector potential. But let's make another assumption, that the wave function is rigid. So if I turn on the field, it will not modify the wave function. So if it happens, you see this guy here will be exactly this one, which is zero. So we can say again that Js is proportional to the to the vector potential. So all these ways to see what is going on are compatible with this London equation. Right? So it's quite powerful. And that's another thing that we can do here is to assume that you have a sort of a ground state wave function of n particles, n electrons, for instance. And now what we're going to do is to describe a sort of current carrying wave function. So what we have to do is to multiply this psi naught by a phase, and this phase is describing the whole condensate of electrons moving with constant velocity. But mind you, it's since we have those formal equations relating current densities to fields, and these local relations have to be translated by the penetration depth. So in this sense, what we have to do is we have to generalize that to position-dependent phases, right? Because the current must obey also that sort of relation. It must be close to the surface of a superconducting wire, for instance. And so, when we do that, we say that now, I presume my wave function now, psi, is just describing this moving ground state. And let me try to compute the density of particles, which is the average of the sum of k of delta functions. And these are the wave functions I'm talking about here. And the current density will be given by this one here. Right? That's straightforward from basic quantum mechanics. And so if we do that, we can write the following. We can write if we apply that to the wave function that I have just written, we can say that the J of R is something proportional to n and the gradient of that phase. So that's a very simple equation relating the superconducting current density to the phase of the wave function. And now, if we just write down the resulting density from the former slide, we have that it will give us n times these n minus 1 integrations of the product of the wave functions. So if we assume that the wave function is just the product of non-interacting particles, for instance in the condensate, like a Bose-Einstein condensate, what we have is that these functions, these are just single particles, single particle wave functions occupying a common ground state. Then we have immediately from this expression that's given by n times these psi star psi. So it's just a sort of a new wave function with a new normalization. What I claim is that I can always describe my superconductor by a wave function which is given by this amplitude and a phase. And so, by the rigidity of the wave function, we can say that if we disturb that, it will be basically the same. But if we start to increase the temperature, we start to deplete these sort of Bose-Einstein condensate of these particles that I showed you up there, right? And if we do that, so that's a very good description of what's going on, because I'm saying that describing electrons by these wave function there. So if we were talking about bosons, it would make sense. But now with the electrons, it's a bit tricky. So let's try to explore that a bit more. And I will define something from the expression that I showed you before, which is called the one particle reduced density operator at zero temperature. And this sort of operator here is given by n times these n minus 1 integrations And instead of having R here, like for N, what we have is R dash. And so, in this way here, our density is just a diagonal operator here. When these R and R dash are equal, so we have a density. And this is quite useful if we want, for instance, to find the average value of one particle operator, say the number operator or the kinetic energy of the system, any sort of one body operator. We can describe the n-body operator by the sum of single particle operators. We can describe that by the trace of n1 and the one-body operator. So that's basically what we have. And again, with this expression, all I'm doing is the same I did before. The only difference now is that I'm creating something else, which is this reduced density operator of one particle in a system of n particles, right? And fine. So how can we fix what we have for, or adapt what we have for the electrons? And the idea is the following. As I define the one particle reduced density operator, I can also define the two particle reduced density operator. And this guy here is given by xy, x dash, y dash, n minus 1. And now I integrate over n minus 2 particles. And I can always do that. I can always interchange all these positions of the particles in the wave function. Because every time I do a sort of exchange here, I'll do the same on the other side, and they will compensate. So it can be a fermionic or bosonic wave function, blah, blah, blah. And so these guys are very useful if I have a two-body operator, something like the interaction between particles. So the full potential energy between two particles will be given by something like this. And I can use this reduced density operator for two particles in order to find this average value of the full internal energy of the system, interaction energy of the system, right? So, now let me assume something else. Now, instead of just a single particle wave functions, what I can do is to assume that this operator, this wave function here, is a product of fully anti-symmetrized wave functions of single particles. And if we do that, I can say that my reduced density operator of two particles is diagonal form x, y, y will be given by something like this. Now, okay, I have two variables, and it reminds us, of something like the wave function of two particles only. And so I can always say the following. Let me choose the sort of center of mass and relative coordinates here. And when we do this, we have that our one particle reduced density operator is given by this expression. So I can integrate over the center of mass for the relative coordinates. And if we have a system which is translation invariant, which is really the case of a superconductor, right? Superconducting condensate, it's translation invariant. And so if we do that, we can split this wave function into, something related to the center of mass and something else related to the relative coordinate. And then we can say again that this density of particles is given by something like this. But this time, so it's exactly the same expression as before. The only difference is the interpretation. That we say now that it refers to the center of mass of pairs, for instance, right? So that was a modification that we introduced. And in this way, so I can go on working with something like this, that is not exactly a wave function, it's just an approximation that I can split something which is an operator. I will split that into in a product of two sort of pure state, right? So that's what we do. And that you'll see that this is quite useful for the rest of the lecture. And again, and this sort of thing you can always generalize to finite temperatures. Because I don't need to say that we are in the ground state. We can define this reduced density particle or two particle reduced density operator by just establishing a sort of rho, creating a density operator for our system. Instead of psi star and psi, what I do is to make the exponential minus beta, whatever, and I can create the density operator for that. And again, you can follow the same sort of steps and get something like this. But of course, it's a bit strange because if I generalize to finite temperatures, this guy here will be temperature dependent. Right? So, and that's something that happens that many times we can play with this wave function as a genuine wave function, but in other circumstances, it's much more appropriate to talk about the other parameter and really to think about the sort of Ginzburg-Landau approximation and so on and so forth. But for our purposes here, I will still regard it as a sort of wave function for the condensate of the system. And again, generalized to finite temperatures, I can easily say that the sort of condensate will be depleted. And when we put particles in the excited states, we can have the so-called two-fluid model that the total current density will be the current density of super electrons or Cooper pairs and some normal electrons. We always have this composition. So all these particles that are depleted from the ground state, they will occupy some excited states, and they will be normal electrons, only normal current. And okay, so but that's not the whole thing. Let me just give you a reference, a very old one, and the guy who introduced this idea of reduced density operator of one or two particles and so on and so forth, and treated the superfluid and superconductors on the same footing was C.N. Young. And what he says is that these guys, or the two particle or one particle, these are operators, and these are emission operators. They can be diagonalized. So what we're talking about is a sort of eigenstate of these operators. And this eigenstate, depending, there is a condition for these eigenstates to have a huge macroscopic eigenvalue. So the number will be quite large in this case. And so in order to do that, what we need is this sort of off-diagonal long-range order. And this sort of thing is what you need in order to diagonalize operators and end up with something like very huge eigenvalue for these operators. Now, okay, so let me try to give you some applications of this approach. So, as I've written before, so we can say that if we apply P to the wave function, and that's the sort of relation that we have. Mechanical momentum plus the field momentum will be given by h bar, the gradient of the phase. And then we can integrate from 2 points here, right, in the ring. So this mechanical momentum, so the total momentum, and that will be given by what? That will be given by this phase difference between 2 points. Now, if I close the circuit, what we end up with something like this. This guy is related to the superconducting current. This is A, and now what we have here is that I leave this point and I come back to the same point, and we're talking about the phase of the wave function. So it's the difference between them is really 2 pi n. Right? So that's what we have for the difference of the phase. If we leave one point, we come back to the same point. And so in this case here, And that's an experimental result. The point is that it was shown, it was measured actually, that in order to fit experimental results, what we need here is a charge 2e. Basically, that's the only place where we really need the specific value of the electronic charge, of the supercarrier charge, which is twice the electronic charge. And if we do that, we say that now, what happens here is that since we have a thick, this ring is thick, we can say that the J inside, deep inside the ring is 0. So this guy here, ABR, is basically the flux of this magnetic field, which is n phi naught. So the flux inside the ring will be quantized in unities of phi naught. So that's what happens to the superconducting ring. And that's a very nice phenomenon, flux quantization. And the other one is the so-called Josephson effect. And for the Josephson effect, what we have is that, again, we have a junction here, two superconductors, and we have a junction. And so we have a wave function on side 2, and another wave function on side 1. So K refers to 2 or 1, and then we have the Schroeder equation for the Lexus here, Schroeder equation for the Lexus there. So in this case, we're talking about a pair. And there is some sort of overlap between the wave function here and the wave to the other side, and the wave function here to the other side. So these are the coupled equations. And so if we just apply that to this sort of wave function, we have this sort of relation here, right? This relation for theta 1 and this relation for n2. And so we can replace 1 by 2 and 2 by 1 and get a pair of equations. And from this pair of equations here and here, we get this sort of a relation, which is the current flowing from one side, which is given by this n2 times the charge. It will be given by the sine of delta theta, but delta theta is just the difference of phases between one side and the other. And this I naught, which is a critical current, it depends on the overlap of the wave functions on one side and the other. And this E2 minus E1, so the difference in energy, is related to the twice charge and the potential, the electric potential across this junction. So from here we can see that if there is no voltage, this guy is 0, so delta theta is constant. And then we can say that there is a possibility of having a current flowing from one side to the other, and this guy depends on this difference of phase from one side to the other. Right? Okay, so now I will try to mix these two phenomena in order to get the first device I want, which is the so-called superconducting quantum interference devices, the squids. And so what we have now is the ring, but the ring is not thick anymore. It's closed by a Josephson junction. So what I'm going to do is to put these two things together and see how the presence of this junction here will change the flux quantization. So that's what happens here. Again, I'm going from point 1 to point 2, deep inside the ring, and so we can write this equation here. So again, super current and phase difference, the gradient of the phase, and vector potential. So again, this guy here will be 0 since it is deep inside the thick part of the ring. And then I can relate this ADR, and another thing is that since this A is continuous, what we have is that this guy is related to the flux. So all I have to play with is this integral from 1 to 2 of this gradient of the phase. So this guy here is given by this integral here of the contour gamma, and the closed contour, and instead of the integral from 1 to 2 to 1. So I'm just taking from this closed contour this contribution here. And so we can say that this guy here gives us 2 pi m. This one will give us the gradient phase, and again we have this integral. And then when we plug it there, and we end up with something like this. The flux will be given by the phi naught by 2 pi and the phase difference between the terminals of this junction and the flux quantum, n times the flux quantum. And so if I have delta theta 0, I recover exactly the quantization of flux. But in this case, this guy here is not 0. And the total flux is given by the flux provided by the external field and the total current in the flowing along the ring. And we can replace that by something like this. So I have a current, since we have this two-fluid model, and so there is a sort of ohmic loss here, and I replace this possibility by resistance. There is a polarization. We have some sort of finite capacitance. So we have a polarization charge here, and we have this so-called Josephson current that we just induced. So, these are the 3 elements that show up in the junction. And if I replace that by, for instance, this I naught sine delta theta, and this ohmic current, and this CV dot, which is the polarization current. And now, if we use that Lenz law, we can write the full equation for the total flux in the ring as something like this. And so if I define a sort of electromagnetic potential energy given by that only function of flux and the external flux, we write this very simple equation of motion for the flux, the total flux inside the ring. And you see, this depends also on the, that defines the current there, the total current. And this guy here I can control, because that's the external field times the area of the ring. So this is controllable by the experimentalists. So we can just change this phi x and see what happens to the total flux inside the ring. And or we can see what happens to these electromagnetic potential energy. And so, again, that's the form of the potential energy. And we have this parameter. When it is greater than 1, we have several minimum for this function. And it's less than 1, only 1 minimum. And so we have many possibilities, just changing this external flux. And these are the following. When we have this 0 flux, we have completely asymmetric potential. And as we start to change it, we can go to, for instance, phi naught divided by 2, and then distort the potential in such a way that I have a bistable potential for the flux. And if I go to phi naught, but we have something like this. So what was the stable configuration for 0 flux will be bistable here and will be a metastable there. So we can play with all these things here and see what sort of dynamics we have for the flux in this highly non-harmonic potential. And moreover, just putting numbers there, 10 to the minus 10 henries, the capacitance of 1 picofarad, and for instance 10 microamperes. If we play with this, actually the capacitance can be much lower than this. We say that this frequency of oscillation, about one of those minimum, will be something like 10 to the 11, right? So square 10 to the minus 27. So if I take h bar omega divided by k Boltzmann, it will be just about 1 degree, sorry, 1 Kelvin. And then we can easily reach these very low temperatures below 1 Kelvin. It's very easy to get in any good low T lab. Then we see that we're talking about the effect, the quantum mechanical effects on phi is basically the quantum mechanical effects of the electromagnetic field subject to the boundary conditions given by the superconducting ring. So that's what it is. And now we can test energy level structure, we can test decay by quantum mechanical tunneling, coherent tunneling, all these sort of things, just regarding, for instance, my particle as my flux, as the coordinate of a particle that can jump from here to there, coherently, from one side to the other. And what about the decay here? Can decay, quantum mechanical tunneling. Great. So, let's start get a nice picture. We'd like to see what really happens in terms of the electromagnetic field, how we operate with that, how can we interpret this quantum mechanical tunneling. So let's think about the condition when we have these bistable potentials, right? So what happens in that case? What happens in that case is the following. We suppose we have this the ring, we have the flux inside the ring, and now we wait for some time, and then we start to see something like this. The flux line in, the flux line out. Flux line in, flux line out. So that's what happens. So that's exactly the, so we change one quantum flux from one of these minima to the other one. So we're really talking about something like the dynamics of fluxoids in this ring. And so this guy here is representing just the heat released by the normal current through the ring. Okay, so and now I can come back to the junction, and I can define, just a new variable here, this var phi, and let's think about the squid again. But the squid now has infinite inductance, so I will take a new squid, and I will fix this phi x divided by inductance will be my external bias of current. So what I have here is just a bias system along this junction, and now what happens is that instead of that potential that we have, parabolic, with these wiggles, what we have now is something like a washboard. So it's a sort of linear, it's a cosine of this phi variable. It has to do with this phase difference, right? And as I change the bias, I can deform the potential. And the equation of motion for the phase, this new variable, is something like this, right? And very similar to the other one, with the difference that now I'm talking about not flux, but phase. And so that's the picture that we have. And that's the so-called Josephson coupling energy, which is phi naught A naught divided by 2 pi. Great. So very similar to what I had before. But now is a potential like this. It's a cosine that I can tilt. Just changing the external current, I can tilt my external potential. And so I can make these two guys here, this maxima and this minimum, these two guys, maximum and minimum, they can coalesce. And if they coalesce somewhere, I will reach this I naught. So that's exactly when we reach this point here. We can just roll downhill to this sort of finite voltage state. Right? But, mind you, we can keep this barrier very low for a long time and ask what's happening from thinking about the quantum mechanical system. So this phase will jump to the other side. So I can either destroy this state by reaching the I naught, the critical current, or I can tunnel through the barrier, or for finite temperatures I can also jump for thermal activation. I always can reach these sort of things by thermal activation. Right. And so, in the same way that I described fluxoid tunneling, I can also think about what happens here. So I have a wire, or just a two-dimensional system, and a current here. And if you have current, we have the flux, magnetic field here pointing outwards and inwards, right? And so if I move this guy along this junction, so what will happen, we can compute this change of the phase of the wave function when it crosses the junction. And that's what happens. When one flux line crosses, we have the difference of 2 pi. And that has to do with this theta 1 minus theta 2 from the upper path or the lower path. And in this case here, this guy must give 2 pi. So the time derivative of delta theta in this case, will give us 2 pi and dn dt, which is the number of lines crossing. This phenomenon is called the phase slip. So then we can generate a voltage just to see these guys crossing the junction. So when we tilt that potential, what's happening is that many of these lines jump from one side to the other. But again, if we think about that quantum mechanically, what will happen is the following. For instance, we have given current here, and we have these lines, inwards, outwards, and we can increase the current at the expense of one line crossing the junction. So we can do that many times, and that's exactly the particle rolling downhill in that sort of washboard position. And so that's the so-called quantum phase in this case. Now, completing this sort of description of the junction, what I've done was really to think about this Josephson junction, Josephson energy, much greater than the capacitive energy. But we can have it the other way around, because we can reach very, very low capacities, 1 femtofarad, for instance. And in this case, what we have is that this term here will be much more important than the potential energy. So, what we can think now is something, because beforehand, what we have is a sort of periodic potential that I can tilt, changing the current. But that's exactly the same as a solid, 1D solid, that I can turn on an electric field. And again, I'll see tilting of the potential. But we also know that we have another description for that. Instead of real space, we can go to K-space. And when we go to K-space, we have to apply this, now, the Bloch theorem relating to electrons in a potential, in a periodic potential. And so, what happens here is that I replace charge by wave number and phi by position. So that's what you have in solid state, in a 1D potential, periodic potential. So, but now we're talking about charge. We can, instead of changing K, I can change the charge, just turning on a sort of gate voltage, the junction, and we can start to feed electric charge to the junction. And so what happens now is the following. I go on increasing the charge in the junction, and so that's the picture that we have here. So we have for this UN, which has the periodicity of the potential, we have this new Schrödinger equation. So we're changing this Q here. So we're changing this gate number. So that's related to the gate voltage. So I can change that. And I have these crosses here, right? Every time this is 0 Cooper pair on one side, then I have 1 Cooper pair, 2 Cooper pairs, and so on and so forth. So when I reach exactly 1 electronic charge, we open up a gap here. So that's the band structure of the so-called Cooper pair box. So that's another description of what we just seen in terms of tilting the potential, or we can just change the charge in these capacitor plates. Now, okay, I'm talking about vortices in these systems, right? In these devices. So what about vortex lines in superconducting bulk? So I'm really talking about now a cylinder with a field, and then what we know is that there are 2 kinds of superconductors, type 1 and type 2. And type 2, what happens is that I don't need to reach the critical field, but even before that, there are some flux lines penetrating the sample. So that's my picture here. I can create a lattice of vortex lines in a bulk superconductor. So I can play with that. I will go fast here because we have this. I want to estimate the size, for instance, of the Cooper pair. We have 2 lengths in a superconductivity. One is the penetration depth, London penetration depth. I showed you in the very beginning. And now we can also try to estimate the so-called coherence length, which is the size of the Cooper pair. And so if we have a gap above the ferrous surface, we can estimate the size just by using this differentiating today and saying that delta P will be given by twice delta, which is the gap, superconducting gap, and the ferrous velocity. And then by the uncertainty principle, we can just estimate this length. So we can compare that to the penetration depth of the superconductor. And what happens is that when this guy here is pure metal, we have this type 1 superconductors, and then, that's exactly when you have full expulsion of the field. Otherwise, we have this so-called type 2 superconductors, and that's when we have very, very fine lines. And in this case here, so lambda is much greater than the coherence length. London theory, as I showed you, is much more appropriate to this kind of superconductor. For type 1 is something else. Right? I don't want to address these sort of issues now, but so that's what happens. For type 2 superconductors, what we have is this. Then we can analyze that, and for type 2 superconductors, what happens is that these flux lines, they can penetrate the cylindrical sample, and it will, for a type 2, it will attempt to have as many lines as you can. But the point is that you also have vortex-vortex interaction that will just make it stabilize as a sort of lattice of vortex lines. Just a sort of, general idea of what happens. Then we can write the full energy, the line energy of this vortex line, and we can distort that. And you can analyze all possible interactions that we have. For instance, we can have a Lorentz force, we can have this Magnus force, which has to do with the superfluid velocity around the line and the velocity of the line itself. So there is a Magnus force there. And we also have some Hall and dissipative effects. And so that's a whole mess, right? And I don't want to disturb you with all these physics of vortex lines. But the final result is the following, is that in the end of the day, when we have something like this, so the inertial term, then we have dissipative term, Hall term, something like the distortion of the line, and then we have these lines can be thin by impurities and many other defects in the material. So, you see, there is a sort of functional, which is the Hamiltonian of the system, that depends on the configuration of the line. And the configuration of the line is just the transverse displacement of this line. And there is a sort of external potential and this Lorentz forcing. So what we can do is that we have a cylinder. I can just try to send current through this cylinder here, right? And so there will be a Lorentz force acting on each vortex line. And if this line is in, it will try to lead the spinning. So energetically, that's what happens. I have something trapping the line, and then you can distort the line, and make it jump to the next minimum, and then you have a sort of nucleation process in the spinning. Okay, now I'm going to finish now with these. We'll be talking about macroscopic quantum. And in many books, you will see that the idea of Bose-Einstein condensation or superconductivity, people always call that macroscopic quantum phenomena. And the question is, these are not really macroscopic quantum phenomena. What we have is that we only have one state, and that's the state of the Bohner state, and that's macroscopically required. Fine. The question is, we have another kind of quantum mechanical states, namely the ones I have just addressed, some of them at least. For instance, when I talk about the squid, let's analyze that. When we talk about the squid, we're talking about the initial state, which has the state of the electromagnetic field and the electronic state. Right? Is that proper state? And on the other hand, we have this final state, which can be, for instance, I have one state here, which is not stable, and another one which is stable. So what happens is that my initial state decays and goes to the more stable state. And this guy here is the initial state of the electromagnetic field, the initial state of the electronic charges, and these are the final states of the electromagnetic field and the charges. And in the case of a bistable configuration, what we have is that that's exactly that picture of the line jumping from one side to the other. But mind you, when a particle is inside, there is no current. When the line is outside, we have a sort of current. So what's that? We're talking about a macroscopic, distinguishable charge current going this way or going the other way, or staying still. So that's the sort of thing we're talking about. And these, for instance, so that's the sort of Schrödinger cat-like state. That we have a state for the electromagnetic field correlated with the state for this electronic system, and another state. And we have a superposition of these. So that's the sort of state we're talking about. That's a genuine cat state. And it's different from what happens only for the Josephson effect. Because for the Josephson effect, what we need is tunneling of pairs. One pair tunneling is enough. And then you can, well, what about the current? Yes, but the current is one pair will tunnel, the other one will tunnel, but there is no sort of superposition of macroscopic states. So these are two different kinds of states. And for instance, in the case of the phase representation here, again, while we have a superposition of wave function on side 1 and side 1 and side 2, and then what we have is a product of these sort of wave functions. But it's not a superposition. The entanglement in this case here is not the same as the entanglement in the other case. That we really have macroscopic macroscopic current flowing in one way and macroscopic current flowing the other way. Right? So these are different things. In this case here, we don't need that. What we need is just a superposition of one pair on the right side of the junction and the left side of the junction. And so finally, a nice interpretation for what I'm saying is the following. Remember that we are fitting charge in the junction. So if you reach the electronic charge, so it's a Cooper pair here, so it's just half charge here, half Cooper pair charge, so it's electronic charge. So these guys here are completely degenerate. Charge here, positive and negative there, negative here, positive there. These are degenerate. But this sort of configuration I can get in a different way. I can just say that instead of electron E minus E and 0, 0 pair, what I'm going to have is electron minus electron and minus a Cooper pair here plus a Cooper pair there. If we have that, that's the same sort of thing. But when I do that, I pay some energy. Because the guy has to tunnel to the other side. So that's what happens here. It's in this case, we see that we have, that's a non-interacting picture. This one is an interacting picture. So when we reach this point here, you see, then due to the energy cost to overlap, I still have 10 minutes. Really? I didn't know that. I'm speeding up. Okay, fine, but fair enough. People have time to ask me some questions. And so that's it. There is this energy that we pay here, and so as I reach that point, and the thing is, it's very nice to have a look at that regarding, for instance, the adiabatic theorem. So if I change this gate number very slowly, the guy will do something like this. And that's exactly the constant current. It's a sort of Bloch oscillation in terms of phase. Now, if I start to change it more rapidly, what happens is that I can jump to the upper energy band. And when I do that, this phenomenon is well known. Zener tunneling. Zener tunneling is exactly this sort of thing here. So when this guy goes to the other, to this branch there, so what we're saying is that we're rolling downhill. So you will win this first barrier, the second one, the third one, roll downhill. That's what that is. So It depends on the sort of, on the speed you change this gate voltage. So I think that, all right. Tomorrow I will start with the quantum mechanical dissipation. Then it will be more theoretical in a sense, right? And less phenomenology. But okay, still phenomenology, but not as today. And so the thing here is that all these systems I've just shown you always have dissipation taking place there. Because we're talking about superconducting devices. These guys, they operate at finite temperature. You have normal currents. Normal currents will dissipate energy. So we have to understand how to treat dissipation in these systems. Because, you know, as you can imagine, these are very complicated systems. Right? You know, if you want really to treat them microscopically, right? It's a very tough. It's a very tough problem. And so what we're trying to do is to develop a also phenomenological way to introduce dissipation for these sort of systems and see how we can handle them. So I thank you very much. So I'll see you tomorrow.
Thank you, Amir. Questions? Have one here.
Thank you for your presentation. When you mentioned squids, you showed the circuit, LC circuit with a
Okay.
an LC circuit with the Joseph junction, right?
Sure.
Yeah. If you have any small resistance in this circuit, does all the superconducting phenomena, flux quantization, they all vanish, or
We have resistance. We have a finite resistance there in the junction. So I'm operating below the superconducting temperature of the bulk material, right? At that junction, you see, you always, if it is very tiny, you have the penetration of the magnetic field. So this piece of the metal is normal. Since it's normal, you know, it dissipates energy.
even below the critical temperature?
Yes, because you have this, you have the normal fluid, right? And once you have the change in the flux, you have the change in the phase of the wave function from one side to the other. When you do that, you introduce a voltage. And this voltage will accelerate these normal electrons. The normal electrons are there. They are still, no problem. The thing is, you're introducing a V, potential difference. When you do that, you remember my picture. You see lines crossing the junction. When they cross the junction, you create a voltage. When they create a voltage, you accelerate the normal electrons, and then you lose energy. So that's why I have this sort of RSJ model, which has this resistance, the capacitance of the junction itself, and the Joseph's limit.
What about in the ring without the Joseph junction?
Sorry?
In the ring without the Joseph junction, is there resistance?
No, because that's a thick ring, and then, you know, if you happen to move your, no, in that case you don't have it, right? Because, you know, there is no way these normal electrons will dissipate, right? Then what you have is that you just have the normal quantization of flux, and that's all.
Okay, thank you.
Usually what you have is, you start from high temperature, with the external field lowered a bit, and then you can trap some flux inside, and that's the way you do it. And these states are very, very, very long lived. These are metastable states. Remember, in the very beginning I told you that these cannot be the ground state of the superconductors. These n phi naught, these are all not stable states. Only one is in stable state, n equals 0. All the other states, they are not stable states. They will decay, but in the age of the use of
More questions? One back there.
When you were explaining about the local equation, you considered the rigidity of the wave function.
Yeah.
This property is a consequence of, like, it's a property of the wave function? Is it a consequence of the temperature, or is it a property of some underlying Hamiltonian?
It's just depending. If you want a microscopic description or explanation, you have to think about the what really causes this sort of wave function of the state, and that's the electron-proton interaction. So what happens is that your electrons now form a bound state, and this is the Cooper pair, right? So in a sense, you can imagine your condensate being a sort of condensation, Bose condensation of pairs. But that's not the correct way to see them. But then the difference, all these electrons very close to the Faraday surface, they will reduce their energy by a parameter delta. So, if you want to excite your system, you have to take electrons from the condensate to the excited states. So you pay delta of energy, right? Or 2 delta in order to excite your electrons. And in this case, when I say that the wave function is rigid, all I'm saying is that the perturbation is not strong enough. If it is strong enough, it will excite your electrons to the other states. And then, if I, for instance, change my magnetic field beyond HC, which is the critical field, I can destroy superconductivity, right? I will destroy the Cooper pairs. And so what I'm saying is that you are free to change your magnetic field or to introduce any sort of perturbation, and you'll not destroy the superconducting wave function. And even if you think about scattering by photons, in this case, it's not enough to make a jump, this to delta of energy. That's why the wave function is rigid. Of course, if I go beyond, a sort of perturbation theory, or I really act in brute force on the system, it can destroy superconductivity. But all I'm saying is that we're thinking about very reasonable external fields and what happens to the condensate when you turn on your A field. That's all.
Thanks. Just one more question.
Yeah.
When you explained about the flux quantization, you get it as a consequence of the condensate wave function to be single valued, right?
Yeah.
But usually in quantum mechanics, we don't demand the wave function to be single valued. Why it should be in this case?
Sorry?
I mean, in other situations, usually the wave function don't need to be single valued.
No, but well, listen, the thing is that in that case, we have, if you have a single connected system, yes, but that's not the case. You have a hole in your system, right? And so every time you have that, if you make circuit and you change phi, and you can just change it by 2 pi, right? And that's all now. If it's a wave function, you come back to that point. Okay, you can have n equals 0, but you can also have 2n pi. And if you make these 2n pi, your wave function will be the same.
Okay, thank you.
More questions? Oh, one here.
So we know that it is very hard to describe macroscopic dissipative quantum systems, and often one has to make a lot of assumptions and numerical techniques that reduces the applicability of the theory. However, there are a set of tools developed by Feynman, Vernon, Keldysh, and Schlinger, which is like non-equilibrium field theory. And I know that it's very effective for continuous systems to describe superfluidity. And I have no idea if it would make sense or if it has been applied in the context of superconductivity, if it would make sense.
I don't think I understood your question. I think that we will address these sort of things like Feynman, Vernon, and Keldysh tomorrow. Right? That's exactly the thing I'm going to talk about tomorrow. Very, at least sort of alternative way. But as far as the macroscopic quantum effect is concerned, I didn't quite understand what you meant.
Sorry.
What exactly is the question?
Okay. If it makes sense to use field theoretic path integral formulations to describe these systems.
The path integral formulation to describe that, I think you can use the path integral formulation for anything.
Sure, but if it's an overshoot,
Yeah.
if it is useful or if
What's your worry? Is that about the fact that your system is not closed? It's
yes.
an open system?
Yes.
Oh, okay, fine. But that's exactly the point. I want to understand how this external universe is destroying my quantum mechanical effects. That's exactly what I want. I want to describe that. Right? So let's see what happens. Many people think that if I turn on any sort of coupling to the external environment, I will destroy that immediately. It's not true. You have coherence times. It takes some time for the coherence to go away. And that's what happens. That's exactly what I'm going to talk about tomorrow.
Okay, thanks.
Tomorrow I'm going to talk about that. I will show you how we can understand the effects of the environment that I will use to describe these damping effects. And then I say, fine, once you can control that, what's the result in terms of these quantum mechanical effects I'm talking about? And thanks.
Have time for one final question.
Professor, I want to ask, you said that London theory can describe the mechanism of second type of superconductors. So, can we say that it can describe the origin or the mechanism of the superconducting current in the type 2, the high critical temperature superconductor?
Sorry, sir, you asked me about
The second
the
type.
microscopic explanation for the type 2 superconductors.
Yes.
I don't know. No, usually the way to describe type 2 superconductors is really very phenomenal, right? You know exactly the structure. You can describe the wave function component, the condensate, the superconducting condensate. You can describe in a sort of all the parameter waveforms. Doesn't matter. The thing is, every time you talk about superconductors, every time you talk about because of lattice, things like that, is phenomenology, right? Usually, the way to treat that is the Ginsburg-Landau theory, for superconductors. That's the way you can address this question. Now, if you really want a microscopic theory for type 2, I don't know. I don't even know whether you need that, because I think it's quite satisfactory what you know about superconductivity and how you play with these tubes and how you control them. It's even, for instance, one problem that is quite important technologically is the levitation. Right? Levitation, for instance, you need these type 2 superconductors. because you need to pin all these flux lines. And then you can really make the object levitating below the superconducting temperature. And then you can easily describe, the motion of vortices in this sample just by his Boltzmann or any phenomenological approach to that. You don't really need to go deep into the microscopic. Because what's the novelty of the superconducting microscopic theory for these type 2 superconductors? We can discuss that, but that was the question, right?
Yes,
Okay.
actually, because what I know that there is no theory to describe the
No.
origin
Yeah.
mechanism for superconducting.
That's why I said, no, I don't know.
But when you said that London theory described,
Here's Broglie, yes.
yes,
That he does the job. Yeah.
yes,
It's very useful.
thanks.
Let's thank Amir again. Thank you, Professor. And we come back 3:15. Ciao.
Like,